We have seen in a previous lesson that there is a unique circle through any three non-collinear points. So in other words, each triangle is inscribed in exactly one circle, and such a circle is called a circumcircle. So for example, for this triangle here, this will be our circumcircle. Okay, and the center of this circle is called the circumcenter, and the length of the radius of this circle is called the circumradius. Our next result states that the three perpendicular bisectors of a triangle must be concurrent at the circumcenter of the triangle. So to illustrate this, let me start with a triangle which is arbitrarily drawn. And I'll label this A, B, and C. Now, I will look for the perpendicular bisector of, so let's see if this is about half. Then this will be a perpendicular bisector, and let's say if this is about half. This will be a perpendicular bisector, and let's say if this is also about half. More like somewhere here. Then this will be a perpendicular bisector. So all of these lines are perpendicular bisector of the sides of our triangle, and they all meet at one point. Let's call this point O. And now we will try to draw the circle which is centered at O, and let's say it's passing through B, and you will see that this circle will automatically contain all the vertices of our triangle. Okay, so what we have drawn here, we have seen that O is the circumcenter of the triangle ABC, and if I call this circle gamma, then gamma is the circumcircle of the triangle ABC. But this is just an illustration. We still would like to be able to prove that this result is indeed correct. Triangle ABC, the circumcenter is clearly equidistant from vertices A and B. So this simply means that OA is equal to OB, right? Because they both represent the radius for our circle. Now, similarly, well, so we can then conclude that as such, the circumcenter belongs to the perpendicular bisector of side AB. This is a previous result that we've seen. So because A and B are equidistant from O, then if you draw the perpendicular bisector of the segment line, it must contain the point O. Okay. Now, similarly, O is equidistant from B, C, and also A and C, right? Because if you look at OB and OC, they are the same, and then OA and OC are also the same. So a similar reasoning tells us that the circumcenter lies on the perpendicular bisector of BC and AC, which is exactly what we need. So we are done. The following theorem is known as the extended law of sines, and it's stated as follows. Given triangle ABC with circumcenter R, if we write A, B, C to denote the lengths of the sides opposite vertices A, B, and C respectively, then A over sine of A is equal to B over sine of B, angle B I mean, which is equal to length C over sine of angle C, and they're all equal to the diameter of the circumcircle of the triangle ABC. Okay, so our aim here is to show that little a over sine of angle A must be 2r, where r is the radius of the circumcircle as shown on the picture. Now let BP be the diameter through B, so it will be the line passing through B and O. Note that if C was equal to, let me call this point here P, note that if C is equal to P, then the triangle ABC must be right at A. Feel free to pause the video for a second to double check that this claim is indeed true, and in that case we must have that A will be equal to 90 degrees. So to prove this claim, we will break our proof into 3 cases. For our first case, we'll assume that the angle at A is less than 90 degrees. So clearly the triangle BPC is a right triangle. Let's see here. So this is the triangle that I'm referring to. So clearly this triangle is right. Okay, and by construction, BP is the diameter of the circumcircle, so it must be equal to twice of R. Next, I claim that sine of angle P is equal to little a over BP. So let's see here. This is the angle at P, right? And sine is opposite over hypotenuse. The length of the opposite side is A, and the length of the hypotenuse here is a BP. So we should get A over 2R. However, angle A is equal to angle at P. Let's see, what is angle at A? It's this angle here. Right. So notice that they both subtend the same arc, which is precisely arc BC. Okay. So angle A is equal to angle B, and we can then say that sine of A must be equal to sine of P, which is equal to A over 2R. And that's exactly what we need. So this completes our first case. For the second case, let us assume that angle at A is equal to 90 degrees. Then little a is equal to BC, and since BC coincides with the diameter, it must be equal to 2R. Now sine of A is clearly sine of 90 degrees because the angle at A is 90 degrees, and that must be equal to 1 if you remember your basic trig formula. Now little a over sine of A, right, that will be A over 1, which is of course A, which is equal to 2R, which again establishes the second case. Now for the third and final case, we will assume that angle at A is the angle at A is strictly larger than 90 degrees. Now let's consider the triangle B PC. PC is here. P is right here. So we consider the triangle BPC. Again, it must be right at C. So triangle BPC is right at C. Now sine of P would be opposite over hypotenuse. Opposite here is little a over 2R. Next, angle A plus angle P. Notice that angle A and angle P are opposites to each other in the quadrilateral ABPC, and we've seen that opposite angle inside the quadrilateral must be supplementary, so that must be equal to 180 degrees, which means that angle A must be 180 degrees minus angle P. Now sine of angle A will be sine of 180 degrees times cosine of angle P minus cosine of 180 degrees times sine of P. However, sine of 180 degrees is 0. Cosine of 180 degrees is negative 1. So we get sine of P. So A and P have the same sign. So then we can then say that sine of A is equal to A over 2R. And we have exhausted all possibilities. Therefore, the proof is completed. Now, let's consider the following problem. Given an isosceles triangle ABC, choose P on the base BC, and we will show that triangle ABP and triangle ACP have equal circumradii, which is the plural of radius. Okay, so we have, let's say ABC is an isosceles triangle. Let's have the same angle here, and we choose a point P on BC, and we want to show that the following two triangles, which I'm going to highlight here, this one have equal circumradii. Okay. Now we solution by the extended law of sines at vertex B in triangle ABP, we know that AP over sine of angle B must be 2R, whatever R is, where R is the circumradius of triangle ABP. Similarly, we apply the extended law of sines at vertex C in triangle APC, and we obtain that AP over sine of C must be equal to 2R prime, where R prime is the circumradius of triangle APC. Now, by assumption, we know that angle B must be equal to angle C because the triangle is isosceles with base BC. And this means that, of course, sine of B must be equal to sine of C. And 2R prime becomes AP over sine of C, which is AP over sine of B. They're the same because sine of C is equal to sine of B, which is also 2R. So we have now that 2R prime is equal to 2R. So since 2R prime is equal to 2R, it follows that R prime must be equal to R. Next, let R and K denote the circumradius and area of triangle ABC, respectively. We want to show that 4 times the area of the triangle times the circumradius is actually equal to the product of the length of the side of the triangle ABC. Okay. Now, for our proof, I will consider the height of the triangle, which is corresponding to side BC. Then we know that the area, which is K of our triangle, must be A, that's the base, times height over 2. And we know that the height here must be B sine of C. This is done by looking at the triangle AB. Call this here, this triangle in yellow. I'm going to call this here, this point here, X, by looking at ABX. So thus K must be A times B times sine of C over 2, and it follows that 2K will be equal to AB sine of C. Now, by the extended law of sine, C over sine of angle C must be 2R, and this holds if and only if so we will consider this equation and this equation, and then we'll multiply the first equation by the second one, so we'll get 2K times 2R, that'll be equal to little c over sine of B, angle C, times AB sine of C. Now the signs cancel each other out, and we get 4KR is equal to the product ABC as desired. Okay, this completes the proof of our corollary and also the proof of our lesson.